Hey everyone, so today we are going to see one of the very famous or most commonly asked question in a math or you can say PhD interview. So the question is, first usually they will ask you what is a subspace and they will ask you, can you tell what are all the possible subspaces of R2 or in general R3 or in general Rn. Okay, so well the answer is one of the very simple ways one can say there are infinitely many subspaces of R2. But obviously this is not a good way to answer. The interviewer won't be happy. So it's always good to categorize. Okay, so what are the subspaces of R2? So one can say the subspaces are the trivial subspaces, which is you can take a singleton 0 or the whole of vector space R2. So this we call as the trivial subspaces of R2. But obviously we are interested in the non-trivial subspaces. So what are the non-trivial subspaces of R2? So they are nothing but all the, you can take the lines passing through origin. Okay, so if you take any line passing through origin, then it forms a subspace. So these are the only subspaces of R2. There is no other subspace of R2. Okay, so that's a nice answer, but then obviously people expect you to prove it. Okay, so let us try to see a proof. There are different versions of the proof, but I'm going to tell you one of the very simplest possible proof which I know. Okay, so what we will do, we will take, so we know that these are the trivial subspaces. This is the whole of R2 and this is singleton 0. So they are the trivial subspaces. Is a line passing through origin is a subspace? So if you take R2 and you take any line passing through origin, then is this line a subspace of R2? Answer is yes. So see, this is a line passing through origin. So you take any vector over here v bar. Okay, so what are all the vectors of this line? If I call this as L, so what is my L? L is nothing but all the multiples of the vector v. Okay, you take a vector v, you multiply it by a number, so you get all the possible vectors. Okay, if you take positive number, you get the vectors over here. If you take negative scalars, you get the vectors over here. Okay, so if you take any line passing through origin, it is of this form. Okay, is this a subspace? Answer is yes. So to prove a subspace, we need to show that it is non-empty. So is this non-empty? Yes, because 0 bar is in L. Okay, because if you take alpha to be 0, then 0 into v bar is nothing but 0 bar, a property of vector space. So therefore 0 bar belongs to L, so it is non-empty. Now you take any two vectors in L. Okay, so let v1 bar and v2 bar belongs to L. So how your v1 bar and v2 bar will look like? Your v1 bar will be some alpha times v bar and your v2 bar will some multiple, say beta times v bar. Because the elements of L, they are nothing but the multiples of v. Okay, now if you add them, what you get? v1 bar plus v2 bar, it is nothing but again some multiple of v bar. Okay, so again since this addition is a multiple of v bar, therefore addition belongs to L. What about scalar multiplication? So let us try to see the scalar multiplication part. So for scalar multiplication, let v1 belongs to L and let a be a real number. What you want to prove? You want to prove that a times v1 bar belongs to L. But that is obvious. Why? Because how my v1 bar looks like? My v1 bar is nothing but some multiple of v. So v1 bar is some alpha times v. But again, by the properties of vector space, a dot alpha is nothing but a alpha dot v bar. So your a times v1 bar is some scalar multiple of v bar. So since it is a multiple of v bar, therefore a times v1 bar is also an element of L. Okay, so what we have proved, if you take a line passing through origin, then it do form a subspace for R2. Okay, but then question is, if you take any arbitrary subspace, if W is any arbitrary subspace of R2, which is non-zero and a proper subset of R2, then what is this W? So now we are going to prove that this W is nothing but again one of the lines passing through origin. And once we prove that, we are done with the proof. Okay, so first we are proving that any line passing through origin is a subspace of R2. And now if I take any non-trivial subspace of R2, it is nothing but a line passing through origin. So let W be a non-trivial subspace of R2. Non-trivial means what? It properly contains 0. It's a subspace, so it definitely contains 0. So it's non-trivial, so it contains a non-zero vector and it is not whole of R2. What I want to show, W is nothing but one of the lines passing through origin. Okay, now since W is non-zero, so let a vector v bar belongs to W. Okay, so we are in R2, you take this v bar. Now it's a subspace. W is a subspace. So any multiple of V bar will also be in W. Okay, so if you take this implies what? Alpha times V bar belongs to W. Okay, so it contains all the multiples of V bar. And we know that this is a line passing through origin, this is a subspace. So this collection, if I take collection of all alpha times V bar, where alpha belongs to R, this is a subspace, this is a subset of W. So this is a subspace and this is also a subspace. Just now we proved any multiple of a vector is a subspace. So W contains all the multiples of V bar. What we are going to show that these two are equal. Well, one of the reason is one can use the dimension thing. Since this is a subset of this, dimension of this subspace is less equal dimension of this subspace. But both are one dimensional, because see, this is of this subspace is of dimension 0, this subspace is of dimension 2, therefore this subspace is of dimension 1. Therefore W is of dimension 1. And what is the dimension of this? It is also 1, because it has only one linearly independent vector, which is V bar. So one subspace is contained in another subspace and both have the same dimension, therefore both the subspaces are equal. That is one way. But if you don't want to go by dimension, here is another way one can prove it. Okay, what I want to show, these two are equal. Now see, what we will show that W doesn't contain any other vector other than this form. Why so? Suppose W contains a vector, say W bar. Suppose W bar is in W, which is not a multiple of V bar. Means it is not a multiple of V bar means what? It will not lie on this line. That means your W bar is somewhere here. Now W bar is not a multiple of V bar. Okay, doesn't belongs to this set. That means what? W bar is not equal to alpha times V bar for all alpha belongs to R. That means W bar is not a multiple of V bar. That means W bar is not dependent on V bar. That means what? W bar and V bar are linearly independent vectors. That means you have two linearly independent vectors in R2. But any two linearly independent vectors in R2 spans the whole of R2. Because dimension of R2 is 2. That means basis of R2 has only two elements. And in R2, if you have two linearly independent vectors, then it forms a basis. That means it spans the whole of R2. So if you have a vector other than a multiple of V, then your W contains V and W, which are independent, and it spans the whole of R2. That means W becomes equal to R2. But W is a proper subspace of R2. Therefore it doesn't contain, therefore your W bar does not belongs to W. Okay, so that's the idea. You take a vector which is not a multiple of V, but then what do you get? You get that they are independent vectors. That means V bar and W bar forms a basis for R2. That means W is nothing but whole of R2, which is a contradiction. Therefore our W bar is not in W. So if you take a non-trivial subspace of R2, then it is exactly a line passing through origin. And now once we have this answer, one can generalize. What are all possible subspaces of R3? The trivial subspaces are 0 and R3. Then third category is of dimension 1, all the lines passing through origin. And the fourth category are of dimension 2, all the planes passing through origin. And one can generalize so on. R4, in R4, 0 bar and R4 will be there, and the lines passing through origin and the planes passing through origin. Okay, so these are all the possible categorization of a subspaces. So I hope the proof is clear. If you have any doubt, you can ask me in the comment section. Thank you.